All right, so today I'm gonna be going over why do I keep saying fucking man? God damn it. Anyways, I'm gonna be going over the fundamentals of the Game Hacking Academy website. So if you want to go through this with me, you can. By the way, I'm not making these videos for like anyone but myself, to be honest. I just make it to help me learn better. So if you're watching the video and you're like, yo, why the fuck is this guy going so goddamn quick or something like that, it's because I probably already know it. But if I come across something that seems like it might be confusing to somebody that doesn't know anything, I'll explain it the best way that I can, which might not be the best because I'm also learning myself, right? So I would recommend for anybody watching this to do this on your own and just like read it by yourself or read along with me. Um, and find out the answers yourself also. Or if you want to hear me just say if you're lazy as fuck and you want to hear me do it, then that's cool. But yeah, I would say if you want to be learn optimally, I would do it on your own. Okay, because you're your best teacher, right? So, anyways, we're just gonna be going over game hacking. I think I'm gonna go over computer fundamentals probably. I'm just gonna go over this entire page. This thing's longer than fuck. And I'm just gonna make. I guess I'm gonna go over a module a day, kind of like what I'm doing with this learn C++. Just going over let me remember this. Just going over a module or two or three a day. But yeah. Anyways, let me go back to the fundamentals. Okay, so let's just start. A typical computer has several connected components. Among the most important are hard drive, RAM, video card, motherboard, CPU. If you were to remove this side of a desktop computer, if you want to know how to see these, if you just pull up your task manager, go to your process monitor, you can see all of your shit like your memory, CPU, disk, GPU. You can see your Wi-Fi. I'm not gonna look at my Wi-Fi because it has my IP on there. So, anyways, if you were to move the side of the desktop computer, the parts might be placed in configuration like so. For our purposes, we will only briefly address the first four components, and we will focus on the CPU in the next section. Hard drives are responsible for storing large files, such as photos, executables, or system files. RAM holds data that needs to be accessed quickly. Data is loaded into RAM from the hard drive. Video cards are responsible for displaying graphics in the monitor. Motherboards tie all these components together and allow them to communicate. The CPU is the brain of the computer. It is responsible for executing instructions. These instructions are simplistic and vary depending on the architecture. For example, an instruction might add two numbers together to speed up execution time. CPU has several special areas where it can store and modify data. These are called registers. The current instruction being executed. So this is just adding 2 to EAX. So that's how like the syntax works for that. Registers they vary depending on like if it's x86 or x64. It can, yeah, basically the way to tell the difference is if it's x64, it'll be an R instead of an E, and if it's x86, it'll be an E. So it'll be like RAX, RBX, RCX, shit like that. Instructions. All computer programs are made up of a series of instructions. As we discussed above, an instruction is simplistic. Typically only does one thing. For example, the following are some of the instructions found in most architectures. Add two numbers, subtract two numbers, compare two numbers, move to a number into a section of memory, go to another section of code. Computer programs are developed from these simple instructions combined together. For example, a simple calculator might look like this: moves 5 into RAX, moves 4 into EBX, and then adds them together. First instruction moves the value of 5 into the register EAX. Second moves the value of all 4 into the register EBX. The add instruction adds EBX and EAX and places the result back in EAX. Yeah, so just add them together. So this would basically be like, do I want to show you this in programming? Okay, whatever. I'm not going to show it, but if you know anything about C++ or programming at all, this is like just making two integers. So it'd be like int. We'll just say int EAX equals 5 and int EBX equals 4. And then saying EAX plus equals EBX. Or you can say EAX equals EAX plus EBX. And it stores it inside the EAX variable, right? Or register in this case. Computer programs. Computer programs are collections of instructions. Programs are responsible for receiving a value, the input, and then producing a value, the output based on the received value. For For example, one simple program could take a number as the input, increase the number by 1, and then move it into an output. It might look like move input into EAX, add 1 to EAX, move EAX into output. A more complex program would have many of these simple programs inside of it. In this context, these simple internal programs are called functions. Functions, just like programs, take an input and produce an output. For example, we could make our previous program a function that does the same thing. It might look like function add input. So this is just, it's a function called add. It's taking the parameters of input. So whatever you input, it would take input, move it into the register EAX, add 1 to it, then move it into output, stored in the output variable. So if I put in 5, so get stored in EAX, 1 plus 5 equals 6, 6 gets put into output, and yeah. We can make another function that does a similar operation. For example, we could write a function to decrease number by 1. So same thing, subtract, just the exact same thing. But you see this add, sub. All right. These two functions, add and subtract, can then be used to create a more complex program. This new program will take a number and either increment or decrement it. We'll take 2 inputs. A number, a mathematical operation in this case, add, plus, or subtract, minus. This new program will be longer and have 2 different ways it can execute. These will be explained after the code. So it creates 2 functions, which we already saw. Yeah, and then it says compare. So compare operation, whatever this operation is. Jump if equal to subtract underscore number. Add number exit. Subtract number. Takes the input of the number and exits. So yeah. So basically it says jump if equal to subtract underscore number. If it's not equal to subtract underscore number, it would then jump to add instead. So it's either subtracting or minusing, and it'll run through this function, and then it'll exit, right? This code has 2 functions at the top, like we discussed. You take an input and then either add or subtract 1 from the input to produce the output. The compare instruction compares 2 values. In this case, it's comparing the operation type received as input and a value code into the program. If these values are equal, we go to jump to another section of code, jump if equal. If the operation is equal to minus, we go to the code that subtracts 1 from the number. Otherwise, we continue the program and add 1 to the number before exiting. Comparing numbers and then jumping to a different code. Jump into a different code depending on their values, known as branching. Branching is a key component of designing complex programs that can react to a different input. For example, a game often have a branch for each direction a player can move in. Binary, decimal, and hexadecimal. Fundamentally, CPUs are circuits. Circuits either have electricity following them, or they do not. These 2 states can be represented by a binary or base 2 numeral system. In a base 2 system, you have 2 possible values, 0 and 1. Example of binary number is 1101, which this is just 1. So it's just times by 2, by the way. So 2, 4, 6, 8. I guess this would be example. Oh, it's not times 2. What am I talking about? It's to the power of 2. Sorry, I'm fucking stupid. So 2 to the power of 4 is fucking I know. We're familiar with a decimal or a base 10. Number system which has 10 possible values. Example decimal number is 126. Number can be represented. Oh wait, no, I was doing it right, wasn't I? Yeah, I was. Sorry, I never really calculate binary numbers. I haven't looked at them in a while. We can represent the binary number above, 1101, in the same format. Here we replace the 10s with 2s. This is just switching from base 10 to base 2. Yeah, base 10 is our normal system, which is what we all use, which is decimal. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, like it says right here. This is how you calculate it, I guess. So we can be represented more. Oh, well, no, this is how you calculate this number right here, 126. We can represent the binary number above, 1101, in the same format. However, we replace the 10s with 2s. So let me look at this. So yeah, so it goes from right to left. So 1 times 2 to the power of 0, 0 times 2 to the power of 1, 1 times 2 to the power of 2, 1 times 3, 2 to the power of 3, which I'm not gonna bother doing all that. Binary numbers can quickly become unwieldy when they need to represent larger values. For example, binary representation for the decimal number 250 is this shit, which, by the way, if you don't want to calculate this on your own, you can just pull out a fucking calculator and just input, what does it say? 250. And then you can look at binary and just copy and paste. That's what I do. So I don't ever really fucking worry about trying to convert it, right? I just convert it with the calculator. To represent these larger binary numbers, hexadecimal base 16 numbers are commonly used in computing. Decimal numbers are usually prefixed with the identifier 0x and have 16 possibility values, which is it's 0 through F. Example hexadecimal number is 0xa1d, which would be, so this would be 10, 1, I think this would be 11, 12, 13. This would be 13. No idea what the fuck this is. Let's just check it out real quick. So that'd be 2.5k. Okay, yeah. Instructions are represented as numbers, like all other data on a computer. These numbers are known as operation codes, often shortened to opcodes. Opcodes vary by architecture. The CPU knows each opcode and what it needs to do in encountering each one. Opcodes are commonly represented in hexadecimal format. For example, if an Intel CPU encounters a 0xe9, it knows it needs to execute a jump instruction. Early computers required programs to be written opcodes. It's obviously hard to do, especially for more complex programs. Variants of an assembly language were then adopted, which allowed a writing of instructions. They look similar to the examples wrote above. Assembly language is easier to read than just opcodes, but it's still hard to develop complex programs in. To improve the development experience, several higher-level languages were developed, such as Fortran, C, and C++. These languages are easy to read and introduced flow control operations like if and else conditionals. Example, the following is our increment/decrement program in C. In C, an int refers to an integer or a whole number. -1, 0, 1, or 2 are examples. So it's just making, so it makes two functions and does an if statement and with an else. So it just says, so the function add returns the input +1. So you input an input, and then it returns whatever your input is by incremented by 1. Subtract does the same thing, decremented by 1. And then this just takes, so if operation is equal to this, we subtract number, else we add number. All these high-level languages are compiled down to assembly. Traditional assembler then turns that assembly to opcodes that CPU can understand. Operating systems. Writing programs to communicate with hardware is a time-consuming and difficult process. To execute our increment/decrement program, we would also have to write code to handle keystrokes from the keyboard, display graphics to the monitor, build out character sets so that we could represent the letters and numbers, communicate with the RAM and the hard drive. To make it easier to develop programs, operating systems were created. These contain code that already can handle these hardware functions. They also have several standard functions that are commonly used, such as copying data from one location to another. The 3 main operating systems still in use today consist of Windows, Linux, and Mac OS. All these have different libraries, methods to communicate with the hardware. This is why programs written in Windows do not work on Linux. Oh, okay. Let's look. Applications. Operating systems need a way to determine how to handle data when the user selects it. The data is a photo. The operating system wants to bring up a specific application like Paint to view the photo. Likewise, the data is an application itself. The operating system needs to pass it to the CPU to execute. Each operating system handles executing uniquely. In Linux, special executable permission is set on a normal file. In Windows, applications are formatted in a special way that Windows knows how to parse. It's referred to as a PE, a portable executable format. The PE format has several sections, such as the .txt section for holding programming code and the dataset section for holding variables. I'll actually show you that real quick with PE_var. So we have an exe, let's just say injector.exe, right? Just drag it into here. This is what it's talking about, as sections. So it has a text section, data, our data, our resources, relocations. Yeah. Games. With all that out of the way, we can finally discuss games. Games are simply applications on Windows that are formatted in a PE format, identical to any other application. They contain a .txt section that holds the program code. made up of opcodes. These opcodes are then executed by the CPU. And the operating system displays the resulting graphics and handles input like key parses. Okay, that's done for fucking computer fundamentals. Alright, I'll leave this for I guess later or tomorrow. Or my next video. Alright, thank you for watching.